So I only met Pierre Leroux, I think, a total of 3 times, unfortunately. I was looking forward to meeting him a lot more often because he was that kind of person. Just for those of you who might not have known him, just to give you an idea of how much fun he was, I just would say that it was, sort of speaking metaphorically, it was like I'd been sitting in a rather dim office, working on the same problem for maybe a bit too long, which is something we all sometimes have the feeling about. And there's this quite interesting conversation going on in the corridors outside in some foreign language, French, for example. And you know, I was thinking, well, I wouldn't mind joining in on that if I could, but the last time I tried to speak French, everybody said, oh no, it hurts my ears. But then Pierre came in and he said, you know, you need to get out a bit more. You need to get a few dates. We know you're too dumb to learn French, but we can teach you how to speak the language of species and get you interested in all of these problems and get you out a bit. And you know, it was a very refreshing thing to meet him, and it's a great shame that friendship I was looking forward to developing for a long time is impossible. So anyway, now I'll talk about counting, and I hope it won't be too disappointing because I'm not actually going to tell you the numbers of any particular objects. This is a review talk where I just want to say a few ways of thinking. There's nothing new in this lecture for some of the people that are serious devotees of cluster expansions and things like that, but maybe it's useful to people that are newcomers to some of these areas to see some of these things. So let's see if I can move this forward. Let's first think about the connection. Sorry, I'm getting overexcited here. I don't know what the hell's happening. How I did that. It's going alive all on its own. Okay, there we go. So I want to first draw a connection between Gaussian integration and graphs. Feynman graphs, really. So suppose, to warm up to this, that you want to evaluate a Gaussian integral just of one variable. So there's just one variable, and p is a polynomial. And so here's the nice formula, which is called Wick's theorem in the physical literature, but that's just simply the formula that all probabilists know for evaluating the moments of a Gaussian integral written in a perhaps unfamiliar way. The Laplacian that is here, the first thing I should say is that I'm not going to bother you with factors of root 2 pi. So d phi is equal to d phi over root 2 pi to make this formula actually correct. But the Laplacian is just the double derivative with respect to phi. And if you want to prove this formula, well, what does it mean first? It just means expand the exponential here in powers of the Laplacian in a power series. And because p is a polynomial, that power series will inevitably terminate, and so it actually makes perfectly good sense in that formal way. And if you want to prove this formula, all you have to do is to compare 2 ways of solving the one-dimensional heat equation. One way is to write the solution of this equation as a Gaussian integral. That's the fundamental solution to the heat equation. So that's one solution. And the other way to get the same solution is to note that e to the t over 2 Laplacian, if you differentiate with respect to t, as we do here, will give you 1/2 Laplacian of u. And they both have the same initial condition, namely when t is 0, you'll get the polynomial p, and likewise here. And so then all you do is to set phi equal to 0 in these 2 formulas, which is what's going on here. and t equal 1. Is there a t factor somewhere? Oh yeah, there's probably a factor of t missing in here because, as I say, I'm being continually sloppy with normalizations all the way through here. Sorry, but you need it, you're right, otherwise it's not right. Okay, so what about this formula in many variables? Well, we take a finite set of labels, lambda, and we now have a variable phi. For phi sub x, well, I'm calling my labels x because actually this set of labels, lambda, is often a model of space-time in the discrete objects that I'll be talking about. It's a discretization of space-time in the things that I'm coming to in the future. So I'll call it x, although it's a little weird. And there's one of these phi's for each x in your set lambda. So phi is a vector in R to the lambda. And then we need a positive, when I want to define a Gaussian integral, so we need a positive quadratic form, and every such form can be written as inner product of the vector phi in this space with a matrix acting on the vector phi. And the matrices are labeled by rows and columns are labeled by this lambda. And we want it to be symmetric and positive definite. And then we can define our Gaussian expectation, e to the minus this quadratic form, polynomial p, and d lambda phi means the volume form on R of lambda. And again, up to normalization, that's the expectation of a polynomial p. And again, the expectation of p is given by Wick's theorem as e to the 1/2 Laplacian of p, and this time the Laplacian is again double derivatives with respect to the phi's, but one is at x, one is at y, and you sew them together by summing over x and y with these coefficients, and the coefficients here are the inverse of the guy that you put up there. And I won't prove this, but it's the same proof as we had last time, only in many variables. And the example which we have to do right away to check that we got this even halfway correct is to evaluate the covariance of the expectation of the Gaussian measure. So we let our e to the 1/2 Laplacian act on this product of two variables because that's what we have there. It's a polynomial p in our previous formula. And we expand the e to the 1/2 Laplacian, and the first term, which is the identity, drops out because you have to set phi equal to 0. And the next term in the expansion is 1/2 the Laplacian, which acts on this phi a, phi b, and gives you, because of this inverse here, one of the derivatives kills off that guy and one derivative kills off that. And you can do them in either order because the a could be the x and the b could be the y, or the other way around. And so the 1/2 disappears and you get the inverse of a, which is the standard formula for the covariance. So, excuse me a second. I always get nervous. And when I get nervous, then I get my dry throat problem. Right. So, let's do a more complicated example now, which will illustrate the appearance of graphs. Let's look at the expectation of the square of a phi at A with the square of a phi at B. So again, we have to evaluate it with, by doing this Wick's theorem on it. And again, being sloppy about all the combinatorial factors, which are very interesting, by the way, but I want to leave them out for a second, that come up in the course of working out this expansion on that. You can see that because you're going to set phi equal to 0, the only part of the expansion of the exponential that can really give you a contribution is the one where there are as many derivatives as there are phi's. So we need 4 derivatives. That means we have to look at the second power of the Laplacian. So we let the second power of the Laplacian act on this thing here. And again, I remind you what the Laplacian looked like here now. It has this A inverse in it. And so one term that you can get by doing these two derivatives, letting these two Laplacians act here, is when one Laplacian devotes its full attention and love to the first factor, phi squared of A. And then you will get A inverse AA, because one leg of the Laplacian acts on the A and the other leg of the Laplacian acts on the A. And then you've got the second Laplacian doing the same thing to the phi squared of B, and that will give you Laplacian on the diagonal at B. And then, of course, there's a second term with a different coefficient in front of it. This proportionality is some other number in here. The second coefficient will be where this Laplace, first of the Laplacians, divides its attention up between A and B. So one leg ends on A and one leg ends on B, which is why we have an A inverse AB here from there. And likewise, the other Laplacian does the same thing. And then it's natural to represent the result of this by drawing a graph. So the first term here, AA, the AA matrix element of A inverse is being represented. A line represents an inverse of A, and when the line, where the line begins is the first vertex, and where the line ends is the second vertex. So this factor there is this piece here. And then we have another piece of the graph corresponding to that for the same reason. And it's here you see that that's because you have a line representing this factor of A inverse joining A to B from here to here, and likewise another line like that. So you get graph. And then those numbers that I was so sloppy with here are very interesting numbers. They count, they will be numbers that appear in front of the graph that have to do with the automorphism group of the graph and all the rest of it. And it's a natural way of counting graphs going in front of it. So with that example in mind, you can now wonder what else you can count by writing it as a Gaussian integral of some polynomial. And I have to say that I really learnt this from John Embry. I don't think that he was the first person to think of it, but he got me into some of the examples that I'm about to show you. So if you want to count self-avoiding loops,
self-avoiding polygons.
Self-avoiding polygons, thank you, yes. Yes, although I'm trying to learn to talk species, I have bought the book and I am reading it. I still occasionally might call my vertices polymers or do some egregious fault like that. So self-avoiding polygons, there's no structure on these vertices here. I'm going to look at the complete graph on these vertices when I draw these polygons. They're all edges are possible, including loops. And so how do we count these? So these black circles are the label set lambda. And I'm going to introduce this particular polynomial, which is located at x. So this is a notation I'm introducing here. A subscript x tells you what fields the object that has that subscript depends on. And so I'm going to consider 1 plus a half phi squared of x. And then, because actually I don't like loops, I'm going to subtract off a number. And then we'll look at the product of these I sub x's over every label in lambda. And this is a notation I'll use all the way through of raising some object to the power of a set. Just means take the product over the points or the labels in the set.
Sorry, what is this fx bar?
Pardon? Do I have a bar? Oh no, sorry, that bar is a premonition of the future. Yes, leave that out. It's too frightening to contemplate at the moment. So when you use the Wick's theorem on the when you use the Wick's theorem on this particular product, you get the sum over all the loops you can draw in here, which have to be disjoint. Now that loop and that loop are disjoint in the sense that they don't share the same vertices. And likewise that one. So these are all you sum over all the ways of putting disjoint loops inside this set, any number that you want, as long as they're disjoint. And then to each self-avoiding polygon, excuse me, not loop, for each edge you put this weight, the inverse of the matrix, where the edge is a pair of points, so you put the corresponding entry of the matrix in. So that's a nice example. I won't go into, again, I'm sloppy about exactly how these things are being counted and so on, but just a kind of riding above it all presentation here.
So this counts all coverings of the complete graph by disjoint undirected cycles?
Not all coverings, because not every, that's a good question. Let me back up a bit. You see this one here.
What, so
if you'd left out that one and you'd left that out, you would have what you were saying.
Oh, I see.
Including those things. The effect of putting that thing in subtracts out the appearance of all of those, and the effect of putting that one in allows every graph to have coordination number 0 or 2.
Isn't that you can include the effect of the loops in the constant?
Yes, exactly. That is just subtracted off the 1. Is that what you're saying?
That instead of subtracting, you can just imagine that 1 is replaced by 1 plus a minus 1 ii.
Yeah,
So
exactly.
without subtraction, you would obtain morally the same result with the shift of the parameters.
Yeah, okay, that's
so
right.
subtraction is not crucial.
No, but I mean, you're looking at a better way of weighting things, which would be to count something for each edge. I mean, for each vertex as well. You could introduce a way of counting which would not only allow a weight per edge, but would allow a weight per vertex as well.
Yeah, okay.
So the sum over loops is sum over collections of loops.
Yes. Now, suppose you want your loops to be oriented. That you can do too, and that's where the business of complex guys comes in. So oriented loops, I'll just have more or less the same picture. Now you want to allow the possibility that the matrix A is not symmetric. And because then you can have a different weight for the edge going this way versus the edge going that way. And then if you want to do that, you really have to allow the Gaussian, I call this a Gaussian field, you have to allow it to be complex, which just means that it's the sum of a real Gaussian field plus I times another real Gaussian field. And now the quadratic form, you see, by having a conjugate there, then you can distinguish, then if the A is not symmetric, you can see the antisymmetric part. That's the point. And again, you take the same kind of polynomial. I haven't subtracted off something here to prevent self-loops, so to prevent loops, but loops are now allowed. And you get more or less the same formula, but it's now over these things. Now,
Does A have to be Hermitian then?
no, it doesn't have to be Hermitian. All it has to have is the property that the product phi a phi bar have positive real parts.
Oh, I see. So its Hermitian part has to be positive.
Yeah.
definite.
So some of us in here have weird, yes?
So where is this width theorem in the picture? Somehow there is some cancellations, right, in the width theorem. Where what cancels?
There's no cancellations.
Okay.
It's the Wick's theorem.
Just I know it in this Hermitian form.
Yes,
Somehow.
here you see what would happen is you would have a phi and a phi bar that you were doing the derivative with respect to. But there's no cancellations. It counts everything that you get by expanding out this exponential and doing the derivatives. Everything counts with a weight. The weight could be complex if you will be complex in general if you because the A can have complex entries. But it doesn't have to. You could just have a matrix A with real entries, just not symmetric, so that you can see the distinction. You can weight differently the guys going that way from the guys going this way.
May I maybe go back to the two questions that we had done and make a further question? If it is not emission, the symmetrization in the sum, does it project on the emission part or the non-emission part really have a role in the weight?
You mean if you take the inner product of phi with phi instead of phi with phi conjugate? Or do you mean the symmetrization? Symmetrization in the inner product. You mean?
As we are summing over
X and Y, right?
We can do 1/2 sum over X and Y, and also the switches that.
Right.
It's canceling the non-emission part, or the non-emission part really appears.
The non-Hermitian part appears.
Appears.
Yeah, it does appear. It doesn't cancel it. Not when you.
have a d over d phi and d over d phi bar.
The non-Hermitian part will affect the imaginary part of what's in the exponent in that.
Ah.
But, David, I wanted to say something about this condition that the Gaussian integral should, of course, be positive definite. You use that, but then you get two equalities on the other two sides for things that are defined purely combinatorial.
Ah, yes,
Right?
true, yes.
So that once you've established the equality between these two polynomials in A inverse for when where an A is positive definite, you in fact get the equalities everywhere.
Yeah. Okay, coming to this. Now, some of us in here have strange backgrounds. We come out of quantum field theory and things like that. So in the back of our minds, and it might be fun for you to think this way too, there's a particle created at this point and it's making its way over to that point through space-time, but it's being buffeted all the time by these background loops, which are the vacuum. Now, we can count these things too. It's very simple. All you have to do is to open a loop. And you open a loop by putting in we already had that factor there. Disregard this for the moment. We already had the factor I to the lambda, and if you put in these two extra fields, one at A, which is the red one, which is where the particle begins, and one at B, which is where the particle ends its life, you'll be counting graphs of this form. So this means all ways of putting in loops, self-avoiding polygons, and a self-avoiding walk, such that there is no intersection between any of them. Now we have a little joke. I learnt this style of title from Parisi and Sourlas, because they wrote a paper with some title like Fermion's Negative Dimensions, Random Fields, and maybe something else as well. Maybe, I thought I should get into this a bit. This is, suppose you only want self-avoiding walks, no loops. You can do that. But you have to extend your notion of Gaussian integration. I'm just, mostly physicists express this in terms of Grassmann integration, but it's actually just differential forms. If you happen to like those, this is the simplest way to come to it. So we'll do the following thing. We let I be what we had before, but it's a differential form. You add on the wedge product of d phi x with d phi bar x. So it's a differential form. And then we define the exponential of differential forms, again, just by power series. You expand that thing out, but the way you the definition of multiplication that you use in your exponential is the wedge product. So here's the power series expansion, sum over 1 over n. And then you have this, there's the inner product of axy with one d phi, that d phi, and another d phi there, but you slip in an inner product because that's how you multiply these two things together. And again, you multiply them all together by this wedge. And that's a terminating series because if you have only finitely many labels here, you can have at most a top degree form of finite degree.
David, the d phi x, does it have any relation to the phi x? I mean, are you ever going to integrate phi
Yes,
x against
I
d phi
surely
x?
am, yes.
Oh, I see. So I can't, instead of d phi x wedge d phi bar x, I can't write psi x psi bar
Well,
x.
you can, but you'd be going off on an excursion that isn't necessary. There. This is a super expectation is just actually an ordinary integration with respect to differential forms as it's defined in your favorite Rudin, for example. You just have to realize that before you can do any integration here, notice I left out the volume. I left out the d phi's. That's because they're being supplied. They're in here and they're in there. All you have to do is to expand that exponential, like I said you should here, collect it up with all of those guys, and do the integration. The integration here is over R2n, the real and the imaginary parts of all of the phi's, and it will only see the top degree form, the 2n degree form in here. And then miraculously, what will happen is that all the loops that I had, which you get by Wick's theorem, and there is a kind of super version of Wick's theorem, all of the loops that you get will have come well, it'll be 1 plus 1 minus 1 minus 1 equals 0. Those are the negative dimensions of Parisian Saurus. The minus ones come from the d phi's. So if you like to show off at cocktail parties, you say this is supersymmetry, and you hurriedly walk away before someone asks you what that is. And but supersymmetry is an amazing thing because the cancellation of all of the background loops in this formula that you have here is one of the simplest ways of getting the cosmological constant in theoretical physics is the energy of the vacuum, and it has this embarrassing tendency to be way too large. And this is one of the most natural ways to get a small cosmological constant. So that's why I put that in there. It's actually, it is the main mechanism, which is why supersymmetry is somewhat popular among theoretical physicists. Makes the vacuum disappear so that this particle can make its way over there without too much buffeting. Okay.
Make a question on the previous
Yeah.
way of. So you imagine in that integral you do all the Taylor expansion of the exponential.
Yes.
So the formal rule is that if you have phi's without the corresponding differential object, you get 0.
If you have phi's without if you have phi's without the corresponding guys here and here, then you get all these other loops from Wick's theorem.
Well, Wick theorem is written with integral, defi bar, and so on.
Yeah, you should also, if you want to use Wick's theorem correctly when you have this situation as well, you should also have d by d phi and d by d phi bar. You should differentiate the d phi's as well in a formal sense.
When you expand out the super expectation, isn't the point that you have to pair up the fees with the differential form?
Yes,
And if they don't pair properly, you get zero.
that's right.
While formally you can also get that if you do not pay them because you have extra fee, you just get as a result a polynomial in fee,
Yeah.
which is not what you want. In a sense, you also have to take it at fee equals 0 at the end.
Yes, but when you have d phi's as well, I'm not in a position to explain this formula, right here because it would take a bit too long. Let me talk about it afterwards, okay? Because otherwise I have a few other things to say. Yeah.
Would it be wrong to say that the proper formula is exactly that one, square bracket, phi equals 0?
I see. No, this one is correct as it stands, but when you use the Wick's theorem, you have to set phi equal to 0. So Wick's theorem had that set phi equal to 0 at the end. Okay?
And the counting is weak.
The counting is the same. Well, you evaluate this polynomial. This is a polynomial in phi and d phi and phi bar and d phi bar. You evaluate the polynomial. You work out what this is, this Gaussian expectation, by applying Wick's theorem to that polynomial. And Wick's theorem involves differentiating with respect to phi bar, and d phi bar with those a's, and then the loops miraculously cancel out for reasons that are hard to explain right now. Now, the point is that in that last example, if all you wanted to do was to count loops, then what I'm about to do right now would be kind of a waste of time. You might be better off counting the loops directly than converting them into Gaussian integrals and applying cluster expansions to Gaussian integrals. But if you want to count self-avoiding walks, it's much more complicated. Well, no, it's not more complicated, but it's no longer the Gaussian measures that you get out of here. Cluster expansions actually do extend to count, to evaluate these kinds of Gaussian integrals in interesting ways. And so that's what I want to show you. Although that's the underlying text of the message, just to keep things simple, I'm only going to talk about Gaussian integrals without these d phi's and d phi bars in them. So, cluster expansions. Now, when am I supposed to be finishing, John?
11.
At 11, fine, that's going to work. All right. Cluster expansions, I want to start off with I'm going to call this the partition function, the expectation of I to the power of lambda, these things that we've been looking at. And as we've seen, the pressure, well, we've seen that the interesting object is the log of this creature divided by the volume. And we have these Meyer expansions as techniques for evaluating that, but not really for Gaussian integrals so far, only for these hardcore gases. Now, the background to what I want to do now is you should assume that I of x is a smooth, almost constant function of phi of x. Now, I know polynomials like the ones I wrote down don't look like, they do look smooth, but they don't look almost constant. But you have to imagine that there are some parameters in there that make them polynomials that take a very long time to get going, and they like to be 1 for most of their lives. So then you can ask, does the pressure, this combination here, exist as a smooth analytic function of I? In other words, can you differentiate with respect to individual i's in here? In the limit, when lambda gets large, increases to a countable set. That's kind of been the subtext to what we've been doing up until now with all of these cluster expansions for polymer gases also.
And here you have in the back of your mind that lambda is a piece of a regular lattice, and that this covariance matrix A inverse is translation invariant?
Yes. So in the back of my mind now, exactly what you said. Lambda is a subset of the Euclidean lattice, say, or any regular lattice. And also that covariance C is short range, has some good decay properties so that it doesn't really like to connect a point A with a point B, which are far apart in this lattice. And the correlations, which you might be interested, so things like the end-to-end distance of that self-avoiding walk will have to do with putting in an extra phi A and an extra phi B in here, like we had before, but those you can regard as being a result of differentiating with respect to i's at various sites, put in some extra parameters and differentiate with respect to them to generate the phi A's and phi B's. So all of this basically means that I really want to concentrate totally on this object here and these kinds of prove these kinds of properties. And the correlations are obtained by differentiating those objects with respect to individual i's at particular points. Then if you do derivatives, by the way, like second or higher derivatives, you get the cumulants. So there's it's not this expectation, but there's a perturbed expectation where you regard that as the Radon-Nikodym derivative, and you have to normalize by this factor as well as putting it in the top line, and then you've got a non-Gaussian expectations of products of phi's, and when you do the derivatives of the log, actually what you get is the cumulants, and rather than the expectations themselves. And the kind of result you'd like to prove is that these cumulants are are roughly speaking equal to the weight of a Steiner tree with these vertices x1 to xn. The Steiner tree is where additional vertices are allowed as well. And why are they allowed? It's because there are these factors I, which are an interaction, which perturb you away from the Gaussian situation, so that more complicated trees, more complicated graphs simply than just pairing up the phi's can arise. And the simplest dominant graphs that should arise and dominate the result here should be these Steiner trees.
What is it? A Steiner tree is a tree on vertices x1 through xn and possibly others.
And possibly
where the
others.
leaves are precisely x1 through xn.
Exactly, and I say Steiner because really it's the shortest ones that will dominate the result.
Thus you also ask that I as a non-vanishing term which is cubic, otherwise you cannot have cubic lattices.
Yeah, if you want to have cubic vertices, you have to put them in the eye, that's right, yeah.
Otherwise you get a kind of Steiner tree with quartic lattices
Oh,
only.
yeah, you're right, yes, exactly, that's a good point, yes. Steiner trees is misleading in that respect. I said something wrong there. Yes, you would only ever get, extra vertices with quartic legs, exactly right. So we want to think about approximate factorization of this partition function. You see, if you're going to take the log of the partition function, the simplest situation will be if maybe the partition function is so kind and so good-natured that it's just a product over points of partition functions at single points. Well, it isn't, but if it was, then you could take the log relatively easily. It would just be the sum of the logs of the individual contributions from each point. Now that doesn't happen because of the Gaussian expectation, but you can go with a weaker property that Z lambda is a sum over factorizations, and the sum is dominated by fine factorizations, and more explicitly, this is what I would mean. Try to prove that Z lambda is a polymer gas. I'm going to write a polymer gas in this form. You take the sum over all partitions of your lambda, and then for every cluster in the partition, for every set in the partition, not cluster, but every set in the partition, you have a weight. You'd like to show that Z lambda has this form where the weight decays rapidly with the size of the cluster. And you would have different ways of measuring the size of the cluster, for example, the shortest tree that you can draw on it. And then you would want to be really close to that situation. What you would be saying is that the clusters or the sets in this partition which consist of a single point are dominant. Then the Meyer, if you had that situation, you could then use the Meyer expansion. It's very close to being a a polymer gas, this object here. In fact, you'd get a polymer gas if you divide it out by the product of all of the single site clusters. You'd get a polymer gas, and then you could analyze it by the Meyer expansion, and you could learn then that this 1 over lambda, the log of lambda, is analytic in the factors I. And so I'm not going to explain that part because we've been talking about that part up until now, but I want to explain how you could show that the partition function has this form. So let's look into the structure of the Gaussian expectation, and the underlying idea that we've been using up until now is that two body potentials, something is compatible with something else, have nice structures in terms of graphs and so on. And I want to just show you that the Gaussian expectation is also two-body in a certain very natural way. You've already seen it, in fact. So the way we're going to get at this is going to involve forests. So let's look at a typical forest. That's just a set of trees. Here's a set of trees. And then instead of using the Penrose summation, which has been talked about up until now, this is a more probabilistic way of finding a tree inside a bigger graph that's coming up. So we need a probability space. Just the interval from 0 to 1 to the power of edges. These are the edges that I'm talking about are not the edges that I've drawn here, but the edges in the complete graph on these labels. There's the probability measure, simple, the vague measure. And then here's the theorem coming up. There exist Gaussian expectations which are labeled by Forrest, so here's a choice of Forrest, and of point S in this probability space. And there also exist partial differential operators, the plus into the power of F. I'll define that in a moment, just wait on the definition of that. Such that the original Gaussian expectation of I to the lambda is given by this kind of a formula. You sum over Forrest, you integrate over your probability space. These new Gaussian expectations, which depend on the forest you've selected in this sum and depend on the parameter S that this point S that you've selected here, and you have to do these derivatives of the I lambda. It's a quite nice formula.
And this is a general formula that's true when I lambda can be replaced by any polynomial?
Yes, now, exactly. The proof that I'm going to go through in a moment, and everything I've been talking about up until now seems to suggest that I should be a polynomial. And the proof is going to involve the e to the exponential, which will only work when I is a polynomial. But once you've established that this is true for all polynomials, then you establish, since it obviously makes sense on both sides, even when they're not polynomials, you can easily extend it.
I mean, we're not using any specific form, because previously you meant by I lambda a specific polynomial.
Yeah, and now we're not using any, in fact, in this formula here, the only restriction on the I is that it be differentiable, so that you can apply that operator and that this be integrable. Now, here's the important thing. Under the law of this new expectation, I of x, which is in different trees, are independent. So these I of x's that are here, 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 and here are independent of those I of x's there, and that one there, and so on. They're all independent. So these Gaussian expectations, in fact, factor. That whole thing factors, and that's why it becomes a product of those weights, W, that we had in the previous formula. So backing up for a second, sorry about this. I'm explaining how this comes about, because that's the factorization of that expectation that comes from the independence that I was talking about.
So the partition would be the partition of the forest into its vertex sets.
Yes, exactly.
So, sorry if I ask not. This formula is valid if I is an expression with some quadratic form in some polynomial in the quadratic form in phi bar, and the same form in del phi bar. Otherwise, you have also subgraphs with cycles.
Yes, I mean, at the moment, I'm only intending to prove this formula for the case where there are no d phis and d phi bars. But you're right, it applies when there are d phis and d phi bars as well. They don't actually have to be, they don't have to be supersymmetric. You don't have to have this exact correspondence between the functional dependence on phi and the dependence on d phi, actually. You don't even need that.
So I thought if they were not equal, you will get not the sum over forest, but the sum over sum.
No. These forests are completely different from these forests here are a completely different structure from the loops and the self-avoiding walk that I had before. These things are attached only to the expectation, and they are nothing to do with those loops and so on before. This is well, you remember that we have this confusion about whether our graphs are on vertices which are individual edges or whether they're graphs on polymers which are already graphs. It's rather like that again. These are something new, these forests. Now, in order to explain this formula here, how it comes about, so I'm just going to give you a glimpse at the proof. I want to talk about paths through the forest, you know, Little Red Riding Hood and all that kind of stuff. So I'm going to define a map from this probability space, which you remember was the interval 0, 1 raised to the power of the edge set of the complete graph, into itself. Here it is. I need to define it in a way that depends on the f, and the f is this forest, for example. The red part, the red lines are the forest, f, and the green and the blue lines are here for me to illustrate something. They're not part of the forest. So, in order to define this map, I have to take an edge in the complete graph, for example, a red edge could be, and I tell you what the image of the S, there's an S attached to that edge in this space, and I have to tell you what the image S is, and it's very simple, it's the same. But if I have a blue edge, notice the blue edge is running between a cluster of points which are in one tree, joining it to another tree. Well, the S that's attached to that edge by this map is 0. And then a green one, I'm coming to the general definition in a second, I just want to show you these examples first. The green edge, what we do is we take the unique path. So there's always a unique path or no path through the forest, joining the beginning to the end. Here you see there was no path joining the beginning to the end, no path through the forest, which is the red part. But here there is a path, you can go like that, and you look along the you look at the S values, these S values attached to those edges, and you take the smallest of them, which is 0.1. And that's how you define a new S which is attached to that green edge. There was an S already attached to it because it was we're talking about a point in this space, but you're replacing it by a new one. That's this map, by doing this. So the definition is that you start with all the S's that you have in this, for a point in this copy here. You assign a new set of S's by this rule. You take the smallest S you can find along the path joining the ends of the edge, x to y.
So sigma really decreasing with distance, because otherwise you are disconnected or you are connected, but
that's right,
you have
yeah.
enough paths, it's easy that you have a small number.
That's right. Now, by the way, I should say that I don't know, there's a formula I'm going to show you, a kind of fundamental theorem of calculus, and I don't understand it. I know how, if you know that it's true, then it's easy to prove. But I can't say that there's a proper understanding of it, and this kind of recipe here makes me think of something called invasion percolation. I think there might be a nice explanation for this formula I'm coming up with in terms of something like invasion percolation, but I don't know what it is. Now, so here's the formula, Forest formula. And you start with any differentiable function on that probability space, the space of all s's. And then you can write, 1 means set all of the s's equal to 1. And you can write this function at 1 as the sum over all forests. And then you take the you take the integral over just the s's which are in the forest. dfs means, as you remember, my convention was that when you raise something to a power, it means the product over edges in this set here, the forest in this case, of d s x y. And you can integrate over the other ones as well, but it won't depend on them. And then you take the derivative of your function f with respect to the edges that are in the forest, and then you evaluate it at this strange point that I just defined it on the last slide there. This is it's a fundamental theorem of calculus, true for any function. And it has this additional property that which doesn't look like it has any relevance at all to this, but it does to the Gaussian situation we're going to be in a moment. If you have a positive definite matrix, then if you multiply it to form a new matrix by these sigmas, it's still positive definite. So,
For any s.
for any s in that probability space, yes. And that's very important because you see that means that if you modify this exponential that appeared in Wick's theorem by throwing in this extra factor here, you can still realize that that exponential of a differential operator is coming from a Gaussian expectation. So now I can just show
Sorry,
you.
go back a second.
Pardon?
Go back one second.
Yeah.
Are you multiplying the covariance by sigma f of s or the a by sigma f of s?
I'm multiplying the covariance, although it would also be true. I mean, you have to see the proof that when I multiply it, but all that matters at the moment is that any positive definite matrix remains positive definite under this operation.
So in the sentence below, you're actually using it the reverse way. Covariance is the inverse.
Yes, you're correct, right. No, actually, that's a mistake. That's a good question. I think I've actually got an error here. I should be multiplying the covariance, not the A. No, that's all right. Yeah, because it's right, because I don't want to back all the way up, but it was the A inverse that appeared in the Laplacian. The Laplacian had the A in Wick's theorem had A inverse in it. Let's back up for a second.
Originally in Wick's theorem, I thought the Laplacian.
Let's look at this formula. In Wick's
Oh,
theorem.
it's the Laplacian. Oh, it's the Laplacian. It's not the Gaussian quadratic form.
Yeah, so we're going to apply this theorem.
Oh, right.
We're going to apply this theorem to this guy here. We're going to do something with this.
It is.
So let me rush forward where you can actually, I should have rushed forward because you can see this. So, sorry about this. Bear with me. Okay, so I want to prove this formula now. So here's what we do. Remember, in Wick's theorem, we have the Laplacian, and I'm going to write this Laplacian as a sum of contributions from edges. The edge contribution is differentiate with respect to one of the phi at x, differentiate with respect to the phi at y, and multiply by the inverse of a at xy. And then if you add all of those up over all the edges, you have the Laplacian that appeared in Wick's theorem. Now, e to the Laplacian over 2, which is the thing that appeared in Wick's theorem, is equal to e to the Laplacian over 2, but you can throw in this factor of s. As long as you put all of these s's equal to 1, you're still doing your original Wick's theorem. I'm just going to use an interpolation now. You take your function f of s, which I was going to apply the original theorem to be this operator-valued function. So then you apply it, and actually in the course of applying it, you have to do this differentiation of the function with respect to the forest variables. So you have to differentiate some of those s's, the ones that are in a forest that's selected here, and when you do, you will pull down a Laplacian. So now you learn what that Laplacian to the f was in the formula that I stated. It's just these edge Laplacians, one for each edge in f. And that's where I'm going to quit. That's the end. That's the proof.
Any questions?
Yes.
Sorry, I would like if you could come back one slice. Have you comment on the? Well, I think in this formula that, by the way, we call the Brydges-Kennedy formula. It's just once more.
Once more?
Yes. I don't think the C x y sigma is positive, definite. It may be degenerate. It may have zero eigenvalues. For instance, take all the s equal to 1. Then you may have it. What I mean is that it doesn't matter, because when you have a covariance, if it is positive, you can define the corresponding Gaussian measure. If it is a finite dimensional thing, you just would have no density with respect to the Lebesgue measure, because you have a couple of delta functions if you have zero eigenvalues, but it's no problem. You can perfectly well realize a Gaussian process which has a covariance which is definite, positive and not definite, and I think that's the case in many interesting examples here.
Yes, that's true. So I stated it too strongly.
Yes,
It could be positive semi-definite. Yes.
Yeah, exactly. And I think that's what is extremely fascinating, is that when you change the values of S in the matrix sigma f of S, the rank of the matrix changes. And that's therefore one of the aspects which I think is powerful in this formula.
Well,
actually the rank changes.
But what you're saying, I think, is maybe you're telling me something I don't know. I would have said that if the C is positive definite, then this is still positive definite. Do you think that's wrong? I think that's still right, because I think it's, you see, what this is a convex combination of restrictions of C to various subsets. So
no,
I think it's...
What you say is true, but I think...
But unnecessarily strong, yeah, is also true.
That's also true.
Yeah, fair enough,
What if
okay.
the s's are all
Or maybe
zero?
useful.
What if the s's are all zero?
That's okay, then C has become completely diagonal. It's like turning off all of the off-diagonal elements of C, and so only the diagonal ones survive. That's the complete decoupling, giving you the finest. That gives you the finest partition in my original formula.
Sigma f of s xx is always 1.
Yeah.
So, and David, what you...
So, yeah. Okay. You yes.
I'd like to some very analytical question concerning this Commission matrix model. So in your quadratic form, if I would like to have this Commission matrix model, then this quadratic form boils down to this trace of the matrix.
I'm sorry, I'm a little deaf.
The Wick theorem and the Gaussian integration, if I would like to have this Commission matrix model, Commission matrix integral model, where usually the Gaussian integration is defined as, the Gaussian density function is defined as exponential to the minus the size of the matrix of the trace of the square of the matrix of 2
Right.
times the higher measure
Right.
of the matrix.
Right.
So your form is, of course, the very generalized form of this, what I know. So my question is, if I replace your quadratic form, namely the pi, in the product of the a times pi as a trace, then it is sort of translatable Right? So I'm trying to translate your language into
Right,
my
into,
language.
yeah, okay.
Because what I know is big theorem is using this trace of
Mhm.
matrix, not using Laplacian. Of course, the Laplacian, what you have introduced, is in a way equivalent to what I know is if I have this matrix trace, and if I do the big, then I have to apply the source integral instead of the Laplacian, but as far as I see, it's the sort of equivalent or very easier form of your generalized form. So my question is it true? Am I getting right?
I think I better answer you afterwards because, yeah, we're talking about, I mean, it would be possible to apply some of this to Hermitian matrix, but I don't know that it would be helpful. Let me try to answer that afterwards.
For kind of for counting the lattice on a surface.
Yeah, I don't know that I don't know that this is useful technology for that. I don't think it is.
Vincent, are you going to talk about the matrix models at all? Sorry?
I
Are you going
can
to talk
talk
about
about
the
matrix models.
matrix models a bit? So
Yes.
Okay, so maybe Vincent's going to give you the answer to this. Roberto.
I think you can leave it.
Okay.
Let's thank the speaker again.